All right, so in the last video we showed that functions with an isolated singularity at z naught, they come in three flavors basically. Either the singularity is removable, or it's essential, or it's a pole of order m. And so I wanted to practice with you looking at examples and figuring out what kind of singularities f has. So here it's pretty easy to see that f has a singularity at 0. Right now, if we plug in 0, bad things happen. And so f has a singularity at 0. And the question is, what kind of singularity is it? So it's isolated, by the way, because anywhere away from 0, this function is certainly analytic. So it's an isolated singularity at 0. Maybe we should write that down just to start with. So isolated singularity at z equals 0. And to see it, I'm going to make use of the Laurent series expansion. I'll point out to you, though, if we look at this function just from a naive point of view, we would never do that, but let's just say that we did. We might say, oh, look, it should be a pole of order 2 because I see a z squared downstairs. And I'll just warn you, that's a dangerous way to play the game. That's not going to work in general. You can't just look here. We need to be very careful and look at the expansion. There are cases when you can just look, and I'll try to highlight those when we hit those. All right, so I'm thinking about this function f. I'm going to write down, if I can pick a color that I want, let's just do black. I'm going to think about f of z as 1 minus, let's go ahead and expand cosine. So 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, so on and so forth. And then I've got all this over z squared, so let's just put a 1 over z squared out front. That's a little bit kind of messy, but hopefully you can see it. I think we can, yeah, there we go. Okay, and so now let's see, we can cancel the 1s, and then this negative is going to go through and change the sign. And then I'm going to push the 1 over z squared through as well. I think you guys can handle this. So let's see. These go away. They're gone. The z squareds cancel. And so I'm left with, what, 1 over 2 factorial minus, okay, pushing this guy through, I'm going to get a minus z, whoop, that's not what I want. I'm going to get a minus z squared over 4 factorial plus z to the 4th over 6 factorial minus dot, dot, dot. And by the way, we should always, when you're writing down an expansion, you should remind yourself when is it valid. So this Laurent series expansion is valid for anything other than 0. You just can't plug 0 into this, except now we pause and we say, wait a minute. This is a removable singularity because there's no negative powers of z showing up. And so let's go ahead and write that down, and then we're going to see how we can redefine f and actually remove the singularity. So let's just point out that thus f has a removable singularity at z equals 0. Make sure you see why. There's no negative powers of z. So that's the definition of a removable singularity. And in fact, we also can see how we should define f. So we can define f as f of z equals, let's say if f of z, that's a, hold on, sorry. I'm still working on my wigglies. I've never been able to be very good at those, but that's like a, that's not a very good one. Let's try again. Here we go. Okay, it's better, but it's still not good. Anyway, so we can define f as 1 minus cosine of z over z squared whenever z is not 0, because that function, this expression, makes sense when z is not 0. And then we just define it as, as the coefficient a naught, the constant a naught, so I get 1/2 when z is 0. If we do that, then we can say f is actually entire. It's analytic on the entire complex plane. Why is that? Because we removed its only singularity at 0 by defining it that way. So please realize that removable singularities really are removable. When you plug in, when you sort of redefine the function in the right way, then it's gone. It's no longer a singularity. And we saw that, again, not by looking at the original formula, but by looking at the Lorentz series expansion. And we could see how it goes. Okay, so second, e to the 1 over z. We've played with this one before. Let's just write it down real quick. I'm not going to do much here, but you can write this as what? 1 over n factorial z to the n. And already you can see this is going to be an essential singularity. Let's write it out. 1 over 1 factorial z plus 1 over 2 factorial z squared, so on and so forth. So we can just say this function has an essential singularity at z equals 0. And again, essential singularity just means there's infinitely many powers of z in the denominator. There's infinitely many negative powers of z. All right, let's do another example. What about this guy? F of z equals 1 over z squared, 1 plus z. I'm going to write this as 1. You know what? Let's go downstairs with it. I'm going to write this as 1 over z squared, 1 minus z. And so I can write this as 1 over z squared times, well, I'll just, instead of writing the closed form, I'll just write 1 minus z plus z squared minus z cubed plus z to the 4th minus da-da-da-da. I'm just writing down the geometric series, with minus 1 over z. And I end up with, when I push this through, I end up with 1 over z squared, and then I get minus 1 over z, and then I get a plus 1, and then a minus z, and I can keep going as far as I want, but I really don't care too much. I'm thinking about this part, the principal part, and I can see that, oh, look, this guy, the highest negative power of z is 2, so now I know that f has a pole of order 2 at z equals 0. And by the way, since we're here, we might as well point out that the residue at z equals 0 of f is, it's negative 1. So, okay, let's do one more example in this video. These are going to be a little bit longer, I guess, but it'll be less to watch. So let's squeeze in one more if you guys can handle it. I'm interested in this function. And, again, it looks like it might be a simple pole, but we learned from previous examples we shouldn't assume that. That's certainly not clear in general. But I want you to realize that the problem here is that z equals 2. And so I can play around upstairs, and I can write the upstairs as z minus 2 plus 3 over z minus 2. That's all clear. And now what's nice is I can break this up and say, well, this is just z plus 3 over z minus 2. And I don't know if you realize how close we are to being in a very good place. The problem is at 2. And when you're interested in an isolated singularity at z naught, you want every z to be z minus z naught. I never want to see z plus something else or z minus something else. I always need it to come as z minus z naught. So this z is killing me right now. So I'm just going to change it. I'm going to write it as 2 plus z minus 2 plus 3 over z minus 2. And believe it or not, this is the Lorentz series for this function. Now, that might cause us a little bit of angst because there's only 3 terms. These Lorentz series are supposed to be infinite sums in the positive direction and the negative direction. And, well, they are. All the coefficients are just 0. So all the a sub n's, right, here's let's write in pink. Here's a naught right there. A1 is right there. And here's B1 right there. And that's it. So this is the Lorentz series expansion for this function, and that's somehow kind of cool. So we can say this function has, let's actually say something meaningful. So thus, this guy, copy, boom, boom. This guy has a what kind of pole? A simple pole. It's simple because it's order 1. Simple pole, m equals 1 at z equals 2. And, oh, by the way, we should always be thinking about the residue. The residue at z equals 2 of f is, in fact, 3. So those are some examples of the different kinds of things that can happen. So I'll stop this video here. In the next video, we're going to look at a theorem that's going to allow us to compute the residue a little bit easier for poles. So we're going to zoom in on poles a little bit and get some theory there.